Hi, today I'm going to be talking about Physics 2211 Lab 2, which is the motion of a falling object. So first let's start with the introduction. So the purpose of this lab is to understand the motion of a falling object and the forces that act on this object. For example, gravitational force and air resistance. We're going to compare the observed model of motion of the falling object with a computational model that includes drag and with one that does not include drag at all. We will be able to explain terminal velocity with the falling object. As for a preview of our results, the computational model with drag represented with the observed motion of the object better than the computational model that did not account for drag, since drag is a very real force which occurs for objects falling, especially in our case. The first fundamental principle that we need to know is Newton's second law. So we should know that there are various different forces in a system. We can combine all these various forces using free body diagrams to be able to find the net force. The net force is also known as the change in momentum over change in time. We also need to know about gravitational force, which is the force between any two objects with a mass. We can calculate this force on Earth by multiplying the gravitational constant by the object's mass. Drag force is the force that can be known as the force opposite to any object in motion. Drag force depends on velocity. So now we're going to do a tracker video analysis. So our surroundings happen to be the air, meter, sticks, camera, ground, and our system is the ball. So as you can see, our ball moves forward, which is shown by our negative slope in our time versus y position graph. So for our ghost clip code, you might have to look closely, but our g is going to be 9.8. Our j hat, which is a unit vector for the positive y-axis, is just going to be 0, 1, 0 at first. We're not going to have a proportionality constant because we're not accounting for drag. So basically, we're just going to have a net force of 10, 0, 0, and everything is basically pretty standard right now. So this is what our computational model looks like when we run it. As you can see, there's a negative slope. So this is our data comparison with using a line graph. So obviously there's a little bit of a discrepancy from the observed data and the computational model. And we'll go over that in a little bit. So now we're going to do the glow script with the gravity and drag. Our j hat is still going to be the same, but now we're going to have a proportionality constant of 0.007. Our time is going to be less than 0.433. Our W is going to be the negative mass of the ball times the gravitational constant times j hat. And our drag force is going to be negative v times the magnitude of the velocity squared times negative j hat. And our net force is W plus the drag force. Everything else is the same. Pretty standard stuff. And this is what our graph looks like using when we account for drag force. Now we'll quantify that using a line graph. So as you can see, our computational model with drag is very accurate, and it basically is one-to-one with observed data, which is why you can't see the observed data line graph, which is pretty cool. As for possible sources of error, possible error can arise from the differing step sizes. For the computational models, the same step size was used, but for the observed data, I calculated the position of the center of mass at each frame. This could make the observed data much more precise than the models. Which models, if any, predict the terminal velocity? Neither model is able to predict the terminal velocity. I believe this is true by observing the slopes of the position versus time graph. When we take the slope of the position versus time graph, we get the derivative or the velocity, but this is never zero. That's why there's no terminal velocity, because terminal velocity has to be when the slope is zero. So the slopes are always increasing in magnitude. Imagine if the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? Terminal velocity is the point where drag force is equal to gravitational force and acceleration is therefore zero. Therefore, the terminal velocity is the same and is equivalent to the case where the same object was initially dropped from rest. Terminal velocity does not depend on initial velocity. Thank you.